We discussed in earlier videos transforming events from one reference frame to another reference frame. So for an example, we say an event happens here according to the K prime frame. We're able to use the Lorentz transformations to see what that event looks like in the K reference frame. And these transformations include the fact that the speed of light will be constant in all reference frames. And so what we're going to do in this video is extend that concept to, instead of just translating events from one reference frame to another reference frame, we're also able to translate certain velocities. And so what you can think of this as, or one particular example, is if we have a reference frame, we will call this the primed reference frame, being a train, and a little stick figure guy walks from one end of the train to another end of a train. That will be the velocity, the speed of him walking as measured from a person on the train. That'll be the velocity from the primed reference frame. And throughout this whole video, we're going to keep careful track of when we're talking about primed quantities or unprimed quantities, because that's what we're working with this whole time, is translating from one to the other. And so the question is, if the person on board the train is able to measure the guy walking with a certain velocity, what will the person off the train measure the velocity of the person as? How fast will he be moving in the unprimed reference frame? And you'll notice here that this isn't the transformations we derived earlier. This is translating from the primed frame to the unprimed frame, because that's the example we're going to use. So we're translating from right, this is what you measure, and then from that we know what the unprimed reference frame will see in this particular example. And so to use calculus to extend from just events to actual velocities is not too difficult. We use the concept of velocity as the change in position over the change in time. And we have both position transformations and velocity transformations. Sorry, not velocity transformations, time transformations. And I went ahead and took the derivatives of these quantities ahead of time. So here we take the derivative of x because x is changing here. We don't need to take the derivative of gamma because this is gamma here. We have the square root of a constant. We don't take the derivative of that. V squared, that's not changing. V is the velocity of two different reference frames, and C is also a constant. So nothing in gamma we take the derivative of. Again, we take the derivative of x prime because the position will be changing, and the derivative of t prime because that will be changing. And it's the same thing over here. Velocity and the speed of light are held constant, as well as gamma. And a quick side note here, the reason we're using u for velocity instead of v, because in special relativity, v is reserved for the relative velocity of two different reference frames. And u, we can talk about the motion of something as measured from a particular reference frame. So here is the motion of something as measured from the unprimed reference frame. If we put a little prime here and a prime here and a prime here, this would be the measurement of something as measured from the primed reference frame. Again, we're keeping careful track of that. So basically what we're going to do here is find the velocity with respect to x, which is dx. This would be the velocity with respect to x. dx prime over dt prime, well, we know what that is. And it is this guy over this guy. So we have gamma times dx prime plus v dt prime divided by gamma times dt prime plus v dx prime over c squared. And from here we're going to divide both the numerator and denominator by dt prime, and also notice how the gamma factors conveniently cancel out. So we have dx prime over dt prime. Dx over dt is the motion, is the velocity of a particle in the x direction, and here we're talking about primed quantities. So we have the primed velocity in the x direction plus v dt prime over dt prime is just 1, so the v is left alone there. And same thing over here. The dt primes cancel out, plus v. Same thing here, dx prime over dt prime equals the velocity in the x direction. We're talking about primed quantities divided by the c squared. So, for example, let's say we got something in the k prime frame. We have a relative motion of k prime to k is 0.5, and that's our v. So hold on, we'll do it in the same order I wrote it out here. So we want to find the motion of something in the x direction according to the k reference frame. So we're going to we'll draw it down here. So u sub x equals, so k prime is going this way and it launches a rocket out in front of it going at 1/2 the speed of light. All the quantities here I'm writing in terms of the speed of light. Okay, our v here, it's the relative motion of the two reference frame, also 0.5. And the denominator, 0.5 relative motion of the two reference frames. And then the measurement of the rocket as measured from the k prime frame, which is, we said earlier, 0.5 divided by, we're doing it in terms of c, so it would just be 1 squared. So here we have 1 plus 0.5 times 0.5 is 1.25. 1 divided by 1.25 is 0.8. So according to what Galileo knew during his time, you added up 0.5c plus 0.5c, you would get c, but in reality you would only get 0.8c. So I use this example because when I was younger, admittedly actually still older than I should have been, I had this idea to go fast in the speed of light. It wouldn't work. And so you do the same kind of thing here, translating a motion in the y primed frame to the unprimed frame, again going from right to left. Here we take our dy prime, and in the denominator we have gamma. We use the same quantity for time, or the same thing over here, dt plus v dx prime over c squared. Notice how we don't have a gamma in the numerator to cancel out with, but we do this the other step is the same. We divide by dt prime to get units of velocity. So we have u sub y prime, and this little subscript denotes that the velocity is moving in a particular direction. And the denominator is the exact same, dt prime over dt prime equals 1 plus v, and then u prime sub x, because we still have this d sub x prime here, divided by dt prime, and we just get out velocity quantity, divided by c squared. And the z is done the exact same way. I'm going to skip this middle step here and just write out the end, just so we have a complete set of velocity transforms. And this should be u sub x, not u sub z. Like I said, the denominator in all of these is the exact same, except u sub y and u sub z, they have a gamma factor because there's nothing in the numerator to cancel out with. So these are the velocity transformations. So let's do one more example before we call it quits of a velocity transformation. But in this case, so we have the k prime frame, the unprimed frame rather, and this is the prime frame. And so in this case, we're going to have our relative motion going this way. So we're going to say our relative motion, our v for the prime frame is 0.866c, which gives a gamma factor of 2. So let's use this. We'll say this is y, and going this way, that's x. So what's our velocity, our u sub y? How will the guy in the unprimed frame measure the velocity? We'll say he's shooting a rocket perpendicular to the relative motion between the two coordinate reference frames. How will the guy in the unprimed frame measure it? So u sub y equals the measurement according to the prime frame we'll say is 0.5, 0.6 c. And here I'm writing out the c's. We already said the gamma factor is 2, so I'm going to just write this here. 1 plus the relative motion, that was 0.866 times u prime sub x. Okay, and this is where you maybe need to pay more attention, because u prime sub x, how does the measurement from the primed reference frame look? Well, u prime sub x is 0 because we shot out the rocket perpendicular to the x-axis. So this quantity is 0 here, so it doesn't matter. So basically the measurement in the y for the unprimed frame is just going to be 0.3 c. It cuts it in half, 0.6 divided by 2. That's in the y reference frame. You will also have a motion of 0.866 in the x reference frame because you have that relative motion, and so you would use a Pythagorean theorem to actually get the total motion of the rocket, which would be going, you would have to add up this component and this component, 0.866 here and 0.5 here, and that would be the total measurement as measured by the unprimed frame. And yeah, that's how you'd work that out. But just as sort of a fundamental building block for this whole thing, you would use these three transforms, and that's how you get them. So thank you for watching the video. I hope you enjoyed it. Have a good day.